Hi, welcome to this presentation on using spectral methods and the quasi-linearization method, also known as the QLM, to solve nonlinear ODEs. So first of all, what are spectral methods and how do they help us with solving ordinary differential equations? To begin, we're going to assume there is some approximate solution yn of our ODE, where phi-k are basis functions that we're going to choose and ak are coefficients that we aim to find. Then, to find ak, we're going to force our assumed solution to satisfy the ODE at certain points, which we're going to call our collocation points. Then if we'd like to increase the accuracy of yn, we can increase the number of collocation points, i.e. increase the number of places where yn satisfies the ODE, but in return this is going to require more computing power. Now alternatively, we could change our choice of basis to get better solutions, but this is a large area of study, and instead we're just going to look at results from particular choices today. Now, by forcing our solution to satisfy the ODE at a collocation point, we create an equation in the AK. Using all of the collocation points, we'll hence create a set of equations. Now, to be more specific, linear ODEs are going to lead to linear equations, and nonlinear ODEs are going to lead to nonlinear equations, which gives us our first problem. Nonlinear equations are extremely challenging to solve. They need to be solved numerically most of the time. These numerical algorithms require start points, which are hard to choose. And on top of this, nonlinear equations often have multiple solutions, which creates a phenomenon known as aliasing. So let's have a look at an example to illustrate this. So here we're solving the ODE y dy by dx equals x. It has exact solution, which I plotted in red. Now, by using spectral methods, we get three other solutions plotted in yellow, blue and green respectively. We see that the green solution is a really good approximation of the red line, whereas the other two are pretty bad. Nevertheless, they all go through the boundary point, which is marked in blue in the left, and when we put the three solutions back into the ODE, we see that all three go through collocation points, which are marked in orange and blue respectively. So we've got two solutions, but only one of them makes sense. So how can we avoid this? Well, we're going to look to linearize our ODE, and that brings us to the quasi-linearization method. So how do we do the QLM? Well, first we're going to rewrite our ODE as a linear and a non-linear part. We're then going to decide a reasonably good solution, yi of x. We'll talk about how to do that later. After that, we're going to find a first order functional Taylor series of the nonlinear part about yi of x, and again we'll discuss how to find this later. Solving the resulting linear ODE should result in a better solution, and we're going to denote this by yi plus 1. Now in the diagram below, I've illustrated how the Newton-Raphson method works. So we begin by picking an approximate starting point, approximation of our root. We then find the tangent to the curve about this point, i.e. the first order Taylor series of the curve. Then we find where this tangent meets the x-axis, because that's really easy to do. And we see that most of the time, this should result in a better solution. Now, the QLM is basically a generalization, but into functional space of the Newton-Raphson method. Okay, let's have a look at how to find a functional Taylor series. Well, it's going to be exactly the same as a multivariate Taylor series, except our variables are going to be y, y prime, etc. Let's do an example, expanding cos y, y prime to first order about yi of x. So first, we start by evaluating at yi, that's in green, and then we partially differentiate with respect to y, evaluate this at yi, and then we multiply by y minus yi, a bit like you would with, say, a variable x in a multivariate Taylor series, and I've color coded this to match below. Then we do the same but for y prime, so we partially differentiate with respect to y prime, evaluate at yi, and times by y prime minus yi prime. Let's have a look at a practical example. So here's the Lane-Emden equation. So again, we split into a linear and a non-linear part. We approximate our non-linear part about the point yi, and then finally I'm replacing y with yi plus 1 and cleaning up everything here, and you see that we're just left with a linear ODE in yi plus 1. So if I know yi, I can find yi plus 1. which means I just need to decide a start point, in other words, a y0. So how do we choose y0? Well, for general convergence, we just need it to satisfy our boundary conditions. But if we want for more optimal convergence, we're going to require that y0 matches as many functional characteristics as the exact solution does. For instance, having singularities in matching places. So in the example of the Lane-Emden equation, for n greater than or equal to 2, it can be shown that the exact solution should go to 0 as x goes to infinity. So we're going to require that our start point, y0, also has that property. But this is not always going to be possible to do. Let's have a look at the first result. So in green is our iterates, in red is our converged solution, and here we're using a Chebyshev polynomial basis. Now we get fast iteration, and around about 6 iterations are our solution. And here we've chosen y0 to be 1 as it satisfied the boundary conditions. Because it's a polynomial basis, we weren't able to enforce that y0 goes to 0 as x goes to infinity, and because of this, our domain width is limited to around 0 to 10. Anything bigger leads to a blow up in our solution. Instead, we can use the rational Chebyshev functions basis. Here we can enforce y0 to go to 0 as x goes to infinity. And in this example, we're able to find a solution on a domain of around about 0 to 25 without blow up. But again, anything bigger will indeed lead to blow up. So we can do it slightly better. Here we're going to use the domain patching algorithm as well. This is where we take our domain, we chop it up into pieces, and we find a solution on each piece. And then our boundary conditions for each piece are going to come from enforcing continuous differentiability of our overall solution. Now in this example, I was able to produce a result on a domain of 0 to 100, which is much, much better than the previous two. Now, what are the pros and cons then of the QLM? Well, we get quadratic convergence for most cases. We have a method to pick our starting point. And generally, it's very easy to implement in Python. But the resulting linear ODEs can be extremely hard to solve to high precision. The method itself is very unstable, especially on large domains, and it's currently unknown specifically when the QLM will converge. So as part of future research, I'd like to collect a more complete set of conditions for convergence to QLM. I'd like to find other efficient methods for solving nonlinear ODEs with the QLM on large domains.